Hi, my name is Elliot, and this is my Arduino Uno-based desktop timer and alarm. I decided to make this clock to serve as a distraction-free device for setting steady timers and keeping track of the time. The device runs off of a 12-volt power supply and 3 AAA batteries. It has 3 inputs, 2 push buttons, and an incremental rotary encoder, which act as the select, cancel, and scroll controls respectively. The screen has a few different states. The resting state has no menu and functions open, leaving only the time, any running alarms, and the ability to open the menu on screen. Pushing the select button will bring up the menu with the clock's 3 functions. This clock can set the time, set an alarm, and set a Pomodoro timer. Whenever an alarm or timer ends, the clock will play a short tune I created on an online music maker. Now, let's go over the details of how I developed this clock. This is the CAD I created while designing the clock. I'm including the CAD not for you to copy me, but instead for you to see how I approach the problem of securing all of the components into what I consider to be a pretty sleek package. If you pursue a similar project, I recommend that you design it around the components you plan to use, as well as to fit whatever aesthetic fits your style, be that a cube, cylinder, or even the shape of a throwable frisbee. Personally, I wanted a square-angled, simple design with a screen and buttons on one side and the dial on the other, taking up the right-hand side. So, in order to ensure I got that design, I started with just the top rectangular face, and then designed the rest of the clock to fit the components inside, resulting in this interesting, in my opinion, design. To simplify the assembly, the entire clock is made with just 3 3D printed parts. These parts are the rotary encoder knob, the top plate, and the base plate. And then there's also one clear side panel made out of acrylic. All of the electrical components fit inside of the clock, creating a nice dense package with everything well contained and visible through the side screen. I found that designing with components like the buttons and encoder, which were through-hole, made it a lot easier since you just needed to make holes and slots in the case of the encoder for them to sit in, compared to things like the OLED and speaker, which required a bit more of a fancy mounting setup. I definitely recommend trying to do as many through-hole components as you can, just to simplify the process. Having a wiring guide like this can be very helpful both in the planning of a project and in speeding up the wiring process when transitioning from a temporary breadboard setup to a permanent soldered one. When laying out the schematic, I had a lot of trouble finding pre-made libraries with all of the features I wanted. So, I ended up making custom ones for all but the resistors and capacitors myself. I chose the components I did because I am familiar with the Arduino Uno, and all of the other components work well with it. The OLED panel I chose because it's a high contrast device and I only needed a 2-color display for the clock, making the monochrome 128x64 OLED panel an obvious choice for me, especially since I already own one. I chose the audio FX board I did mainly because it does all of its processing on board, meaning that the Arduino only had to send short signals in order to play all of the sounds I wanted. This meant that more of the bandwidth of the Arduino Uno could be used for clock-related things other than sound. While prototyping, I found that the buttons worked much better using ground resistors, so I included those in the final design. Similarly, the encoder worked much better when I included decoupling capacitors to smooth out the signal that it projected. These are not strictly necessary for the clock to function, but they really did help smooth out the experience once I was using it. This is the code that runs the clock. There is a lot of it, so I'll go through it section by section so you understand what's going on. At the top, I include my libraries, and then define the pins, and all the variables that manage the information on the clock. I have a lot of variables, so I made sure to use short ints, booleans, and chars wherever possible in order to minimize the amount of space used for all of these variables. I define an interrupt function for reading the encoder, and then in my setup function I activate the LED and assign modes to all of the pins. Void loop controls almost everything about the clock. In it, there's a timing functionality which keeps track of the seconds that have passed and updates all the clocks and timers accordingly. Below that is my input functionality recording, which involves the encoder and the two buttons. These three functions record in the variables whether the encoder and buttons have moved and by how much. Below that is the grunt of the loop. The UI-specific functionality uses switches to analyze every single variable in order to decide what the clock needs to be doing and how it should do it. This includes checking for button presses that have happened and activating the correct future sequences, as well as updating the time and alarms. Below this large set of switch functions lies the clock maintenance. These if statements are here just to make sure that when the alarms and timers are displayed, the correct one is displayed with the correct time active. Below this is the sound timing. This is much like the timing function at the start, except it records in much smaller increments and is meant to control the sound effects on the clock. If a sound effect has been activated by the UI functionality, then this function will activate the soundboard using a short change to the pins associated with the sound effect. The final section of the code is the drawScreen function, activated every time at the bottom of the loop. The drawScreen consists of a lot of switch functions, all of which contain various display options for different modes of the clock. It displays everything you see on the LED screen, from the clock, the timers, the menu, and the buttons. Of note is the trigonometry used to control the lines on the clock face when setting the time. Otherwise, it's just a bunch of display and draw functions based on the Adafruit library. And that is the entirety of the code that controls my clock. And that just about sums up my desktop timekeeping device. If you want to build a project like this, you can check out my instructions on maker.io, and can access the CAD, EDA, code, and sound files on my GitHub repository at github.com/theholywhale/Arduino alarm clock. Note that the components I've used are in no way the only option. A clock like this could work with almost any common hobby microcontroller, be that a different Mega-based board like the Arduino Mega, or even something on a different platform like the new ARM-based Raspberry Pi Pico. Anything with enough onboard storage, pin space for all the inputs and outputs, and support for I2C or SPI for the display should work. Along with the microcontroller, the inputs are in no way set in stone. You could use almost anything to control a clock, including less standard inputs like an I or receiver and remote, or even clap activation via microphone. Overall, I think this is a useful and fun project to tackle, so I hope it's inspired you to go out and build something for yourself. Thanks for watching, and I hope you learned something.